Started. We are in lecture 11 and making good progress here. We're going to keep talking about the economics of HIV/AIDS today. Problem set 2 will be posted on Thursday, and it'll be due 1 week later. So again, a week after the problem set. Problem set 1 has been graded, and the mean is pretty good. It's about 7.5. Standard deviation like 1.7. So that may give you a sense of sort of where you fall in the distribution. Okay, any questions before I get started? Sorry? Oh, with the mean and everything? Okay. Okay. Any other questions? Yeah. Yep. All right, so let's continue where we were last time. We were discussing this method, difference in differences, and we're going to, in just a couple minutes, apply this to the case of tea pickers in Kenya and trying to understand how disease, in particular HIV/AIDS-related morbidity, affects their productivity. And this was the setup. We talked about how the difference between this regression equation and what we were looking at before is now we have 2 time periods. We have a baseline period, period 0, and we have a sort of follow-up period, period 1. And the event here, or the kind of relevant treatment, is when an individual falls ill with AIDS. And one thing to keep in mind when you look at the Fox et al. Paper, if you haven't read it yet, is the regression they run is a little different. What they're basically doing is they're kind of running the regression we had before that we looked at when we were looking at the deworming paper for multiple time periods, and then they plot out the results. So they don't run the difference in exactly the same way, but you can reconstruct the difference in differences. I'll show you from their data, pulling their data. So this is the regression equation. I think we were just ending up on this slide last time. The difference in differences equation takes the difference between the 2 groups, the treated and untreated, in period 1 versus period 0. And when you do that, just go through the algebra, you come up with the true effect of interest, B, plus the difference in omitted variable bias between the 2 periods. So we were discussing at the end of class last time is how, as long as this difference, even if there is a difference between the treated and the untreated, even if their x's are different, even if there are unobservables that differ, even if they're not exactly the same, we don't have an experiment, et cetera, as long as those differences are reasonably constant over time, they'll cancel out. And that's really what that second term in blue tells us. And we were discussing last time when that might be the case. So when would omitted variable bias not be an issue for us here? Well, we already know cases 1 and 2 we talked about above. If we could collect data on the omitted variables, that's point 1. We'd be fine. Point 2 is if there were no omitted variables, we'd be okay. That's not usually the problem we have. The third solution is using randomization, like we talked about before. But the fourth solution is if we have panel data, in other words, we have information on multiple individuals at multiple points in time, and the extent of omitted variable bias is constant over time, then this approach of difference and differences yields an unbiased estimate of the treatment effect. So there's a couple of data needs that are a little more severe here. Remember the deworming case, we didn't need panel data. We could have just relied on one follow-up survey, and we would have had an unbiased estimate of the treatment effect. Here we need panel data, so there's more severe data needs, and we have to make a stronger assumption, which is this assumption about omitted variable bias. So it's a more restricted method, but it can be useful in some cases. So one of these conditions likely to hold, basically when unobserved factors are stable over time. At the end of lecture last time, we talked about 2 or 3 examples of how they might not be stable over time. Instead of kind of going through those again right now, when we get into the case of the Kenyan tea pluckers and talk about the results and we discuss the setting in more detail, then let's return to that issue once we have a little more detail. So and again, this is the case we're going to be looking at people falling ill with AIDS and looking at their productivity. And the Fox et al. Paper is a very lucky case where we have very detailed information on individual worker productivity. So workers on a large tea plantation or tea estate, as it's called, pluck tea, and they're paid per kilogram of tea. So the company keeps very accurate records of how much tea was plucked because they pay the worker per kilogram of tea. So they have daily productivity measures for something like 10,000 tea pluckers. So it's a huge agro-industrial activity. And then there's another 8,000 workers on different parts of the operation not plucking tea, but they have to package the tea and clean the tea and all these other things. So it's 18,000 workers in this one tea plantation. So they've got lots of data. And what's very nice about it is, again, they have very accurate data day by day on these workers, but it's a kind of well-regulated system. We can understand what the work rules are. Absenteeism is being measured. So we've got good administrative data on a lot of things that we would like. Okay. The big question I want you to keep in mind when we get into the details of this setting is, what are the reasons why the productivity of the 2 groups, those who ended up becoming ill with AIDS and those who didn't, why might their productivities evolve differentially or differently over time? How might these 2 groups have differed? And if we really can't come up with any coherent reason, then maybe the difference in differences assumption is pretty good. But if we come up with 10 reasons and we can't really rule any of them out, then we're going to kind of scratch our heads and wonder about what's going on. Okay, so we're going to focus on labor productivity and to some extent labor turnover as well. This is the Fox et al. Study, again, on these tea plantations. In all, they have an interesting setup, and it's not one that you'll see in the other papers this term, but it's one that you actually see in some research studies. The first thing they do is they identify workers that died or retired due to HIV/AIDS. And the reason they know that these workers had HIV is because the company keeps very detailed medical records on all of its workers. So they're very extensive medical facilities. As I mentioned, there's 18,000 workers. So this is like a little city. And in addition to that, these workers have families who also live on the estate. So there's just tens of thousands of people in this plantation. They have their own hospital. They have multiple clinics. So there's a whole health infrastructure, and all of it is free of charge for workers. So rather than having to go to government centers, they can use these kind of company facilities free of charge. And of course, that's a big incentive for workers, A, to stay healthy and get the health care that they need, but B, it lets the company kind of know what the health status of their workers is. So these 54 workers are workers who got sick, went to a company hospital or clinic, were tested, were HIV positive, and then either died or retired in the coming period after that. There are some data issues here. So they mention this case in the paper. People who start getting sick and for some reason or other don't want to go to the company facility to get tested, well, the company would know that they're HIV positive. And there are reasons why people during the time period they have data on might not want to go to the company. They might have feared that they would be fired. Even though workers who are HIV positive weren't fired, they kept working. We have data on their productivity, but they might have feared they'd be fired. They might have gone to a government clinic to get tested or a government hospital. So they're probably, they're almost certainly missing some HIV cases here. These are just the ones that basically went to the company hospital, got tested, and then eventually died or left work. What they did is for each of these 54 people, who they call their cases, or we would call treatments, these are the affected group, they found 4 workers. They matched 4 workers. So there's a whole approach to dealing with data that's called different matching methods. So they matched workers, 4 workers for each one. Well, it doesn't quite work out to exactly 4. They say 4 in the paper. A little more than 4, more like 5. But, oh no, sorry, it's 4, sorry. This is the total, my bad. This isn't the control, this is the total. So it's pretty much 4 to 1, almost exactly 4 to 1. They found 4 workers who worked on the exact same field that the sick workers worked on. And the reason why they do that is the different fields in the plantation have different soil fertility, productivity. The age of the tea plant affects how much it produces. So they want to make sure that they're really comparing comparable workers who have sort of the same raw material to work with. So for each sick worker, they found 4 other workers who worked on literally the same field, and those are the controls. And in particular, they matched up to 4 workers who during this time period never got sick, were never diagnosed with HIV or AIDS. So these are 4 healthy workers for each sick worker. What do people think of this approach? Are these likely to be good controls, pretty good controls, bad controls? What are the things you'd want to think about or worry about with this kind of data collection strategy? Yeah. So you want to make sure age is similar. In terms of any sort of physical labor, age is a very strong determinant of productivity. You want that to be matched. What else would you be interested in? Yeah. Gender, potentially as well, depending on the nature of the work. There may be gender differences in productivity. Yeah. Other aspects of health. And again, they have all the company records on health, so you kind of worry about those being balanced. Yeah. Yeah, so that's another concern. Maybe, imagine the following. Imagine that there were a small number of workers on each field. In truth, there are many workers, but let's say there were a small number, and they tried to match up weak and strong workers together for some reason. Then, for some reason, you may get some very non-random choice of match sample potential. But my understanding is there's like hundreds of workers on these fields. Yeah. How would they get sick, or just form relationships or something? Or okay, could be. It could be that if you work together, people form relationships and are more likely to be infected. So maybe even, you're raising a point. Maybe some of these controls, even though they aren't diagnosed, maybe they're infected. We just don't know about it. They didn't go to the clinic, the company clinic. Or, yeah, sure. They work together. They meet by working together. Sure. Yeah. So who has a weaker immune system? Which? Mm-hmm. Yep. Yep. Because of what Martine was saying, that somehow they're also infected, you think? So it could, to the extent that the control group is infected, keep that in your mind when we look at the data, because we're going to come back to that, and they mention that in the article. That's something to think about and to keep in mind. Okay, so you guys have raised these issues that, these control folks may just look different than the treatment. This is very different. Just contrast this with deworming. In an experiment, in a randomized experiment, you define the sample, and then you come up with some experimental way to divide them up into different groups. But at the start, at baseline, so we would say ex-ante, they're the same. They're kind of the same population. Here with matching, you're kind of doing the opposite. You kind of identify the treatment group of interest, and then you do your best to sort of bring people in that kind of look similar. But that's a very different approach. And these approaches that instead of ex-ante, finding comparable people, try to get people in ex-post who look similar, are just seen as fundamentally less credible as research methods. So that's a big distinction, but typically in these differences designs, we don't have experimental data to use. That's why we're using these other tools. Okay, so just keep in mind that the whole approach to finding a control group is just totally different. It's totally different here. Okay, so we have our sample. It's not a huge sample. I know that some of the co-authors on this piece, and you might ask yourself, why only 4 matched workers? These fields have hundreds of workers. Why didn't they match 20 workers, for each sick worker? What ended up happening when they started assembling all this data, they were assembling this data in like 2000, maybe 2001, 2002, and there were basically paper records that they were going through. And it was just very time-consuming to literally get daily productivity measures and absenteeism records for all these workers. So because of their budget, they basically said, okay, for each of these sick people, we have enough money, basically, to get data on 4 others. Ideally, with these thousands and thousands of workers, you get a really huge control group. You wouldn't necessarily only match 4 workers. But I think that was just a financial limitation. Is HIV/AIDS very important here? Well, actually, 60% of all deaths or medical retirements of workers on this plantation were HIV/AIDS related. So this was a very salient health problem at this time on these plantations. A lot of the illness on the estate was due to HIV/AIDS. Okay, so you guys raised some interesting issues about sample balance. So actually, here is the population, what they call the cases, or we would call treatment, and then the comparison. So there's 54 treatments, 217 comparisons, and we have the sort of mean and standard deviation on different variables there. So again, we would call the T equals 1 would be those with AIDS, T equals 0, no AIDS. What do people think? Are these comparable populations? Are these pretty good? Just at sort of first glance. Age looks pretty good. 36 average in one group, 37 in the other. So not too different. Which of these variables kind of looks a little bit more different? Maybe gender looks a little bit different. So it's 60% versus 70%. Not huge differences, but some differences. Yeah, they're 5 years versus 6 years. So the cases, the treatments are a little younger, have a little less experience. They're a little more female, basically. That's the kind of the thing. So they're not radically different. What they do in their analysis is they control for these variables. So again, in their regressions, they put these explanatory variables as right-hand side control variables to try to capture any differences. It turns out in their analysis, gender, for instance, has no predictive power in terms of how many kilos of tea are plucked. So that doesn't have much predictive power. Neither does years of experience, it turns out. Now again, the bulk of the sample is 5 or 6 years of experience. You might think that most of the learning curve on experience would be in the first couple weeks or months. So again, years of experience and gender don't have much of a difference. Age has predictive power, and they do. But anyway, they control for these differences in their analysis. So that's good. And what they can't control for are all these other unobservables that may correlate with becoming ill. So if you think for whatever reason those who end up with HIV/AIDS differ in some characteristic from those who don't, then this isn't a great comparison necessarily. Yeah. Yeah. So actually, years of service is significantly different at very high level, at 94% confidence, and the other ones are kind of borderline, but they're not significant at traditional level. So there's no smoking gun that these are massively different, but these are substantial differences, I would say. So now that we've described the setting a little bit, and these guys, they're plucking tea. It requires a lot of physical strength. It requires a lot of kind of focus actually, because they have to just keep going all day for hours, plucking tea leaves very quickly, very accurately. They rip the tea leaves, it loses a lot of value. So that requires certain sorts of characteristics. Are there any individual characteristics that might correlate with becoming HIV positive that you think would affect productivity, and in particular would affect changes in productivity over time? Right? That's what's really going to matter in differences. Yeah. Okay, so you're saying maybe if you're not as well, you have worse health, you may be more, if you are exposed to HIV, you may be more likely to actually become sick or contract the virus. I see. And so maybe your just overall health status maybe as you get into your 30s, those who are a little bit sicker would have had, to start with, would have had a sharper decline in productivity over time. And those who are, maybe you're saying, have a weaker immune system, maybe this gets back to the comment before, they're more likely to somehow end up infected, something like that. So that would be one possibility. What would be another kind of theory or story you could tell about how these things could be linked, especially with changes over time? That's what's going to matter for difference and differences. Could there be something about personality traits or personality characteristics, potentially? Yeah. Yeah. They did. They have data on that. They have a number of dependents. They have marital status. They don't focus on it as a control in the regressions, but they mention in the paper that they have that data. They don't say what they do with it. I mean, the good thing about this paper, and this is written much more as a public health style paper, it's really tight. If you guys have read the paper, it's only 7 or 8 sort of dense pages. In our econ papers, like, we go on for 70 pages, and we extend, we talk about God knows what. So there's some nice things about this paper, but what they don't do is give like the full accounting of all their variables. And so I'm not sure if those are enough. They do have the data. So presumably there were some sharp differences they would have reported. Did you ever hand up? Yeah. Okay. Yeah. Yeah, so that would be one story. One story is there's different personality characteristics. And they don't have data on these folks' personality characteristics, so we can't test it. But one concern would be the following. People, almost by definition, if you're having more unsafe sex, you're more likely to get HIV positive. So this group, the treatment group, is more likely to have been more sexually active. And if more sexually active people just differ in certain ways, they're more social, they party a lot, as you said, they have just a different tolerance for risk, or et cetera, then that would be maybe a fundamental personality difference on average between these groups. And as these folks get into their 30s and they get older, those who've been partying a lot earlier on in life just sort of lose productivity faster than those who were sort of early to bed, early to rise. Maybe that would account for some of this change over time. So that would be one story. And again, we have no evidence for that. We don't have the data here. But if we're going to sort of hypothesize, that would be a story that's a coherent story. There's just different types. Maybe earlier on, when they're younger, they could get away with partying more, being more sexually active. As you get older, you can't get away with less sleep or whatever it is. I mean, that'd be one story. Any other theories or stories about the characteristics of people that might lead to this time-varying shift in productivity that correlates with HIV? Yeah. Okay, so even if they hadn't become HIV positive and gotten AIDS, maybe they would have suffered from the consequences of other types of infection, right? So maybe the counterfactual, meaning what their productivity would look like without AIDS, would have also shown some decline. Okay, so for all these reasons, we might think that you would see some gap between these groups over time, just because different types of people on average tend to get infected or not. There's also, so I think that's a really good way to put it, and maybe you guys can just keep thinking about these cases. In general, in some of the other papers we see this term, when you read research papers or you see research studies in the newspaper that use these kinds of designs, go through this kind of analytical approach and think through the kinds of characteristics that might correlate with treatment and how it might be time varying. That's going to be the key. And that's there's 2 or 3 steps in there. It's non-trivial, but it's a very important exercise. Okay, so this is actually what the data looks like. And let me explain it to you guys. The y-axis here, the vertical axis, is kilograms of T plucked. And you can see on average they pluck around 40 kilograms. But there's some variability. These circles and x's are the average in the sample. The horizontal axis here is years before death or termination, meaning you're forced to retire due to illness, where 0 here is basically when the individual dies or leaves work. And so what they do is they go back, each of these dots is a 3-month period, so a quarter of a year, and they go back to 3 years before the death of this individual. And they could have gone back more, but again, they had limited funding. They could have, the company records go back a long time. They also said that some of the workers had only been working for 3 or 4 years. You saw the average was about 5, so they had some limitations. They go back 3 years, and they get daily kilograms of T plucked for the treatments and the controls, for all 271 people in the sample. And what you're seeing here is the average, the circles here are the treatments, and the x's here are the controls. And they're showing the average of the treatments and the controls 3 years before the individuals died, 2 years and 3/4 before, 2.5 years before, 2 1/4 years before, et cetera, all the way until the death. And what they overlay on that are some fitted plots. These are flexible polynomial fits, maybe 4th order polynomials or something, quartic polynomials probably, that fit the data quite flexibly for the treatments and the controls, for the cases and the controls. Okay, so what do you guys see here? What are the patterns? And looking at the data in this way, do you think that this provides more evidence that difference and difference is a good approach, or does it kind of provide evidence that's not a good approach? What would be your take? Yeah. Sure. So for the cases, for the treatments, you know exactly what this means. This is sort of their data before they die. For each of these individuals who dies, there's 4 people matched to them who work on their same field. And so this is the data for the controls in exactly those same months, matched to each person who died, going back over time. So 2 years before death isn't 2 years before the control group died. They didn't die. It's 2 years before the treatment person they're matched to died. Does that make sense? Okay, sure. Yeah. Okay. Okay, so you're saying, okay, so he's seeing a lot of variation over time. Is the variation over time necessarily fatal, or is it a certain kind of variation over time that's fatal for difference and differences? Now let's go back into let's go back into the regression equation, right? There was period 0, the pre-period, and then there's period 1, the kind of follow-up period. How should we divide up this data into a period 0 and a follow-up period? What would be the kind of rule we would use to make that division?